What we'll do is we'll put the temperature here, and then we'll add heat to this. So we're just going to add heat to something like a block of ice. Let's say I start off with a block of ice at minus 205 degrees C. So it's extremely cold. Well, I shouldn't go that low. The reason I shouldn't go that low is because some solids undergo phase changes. Like, so we could have a solid to solid. You know how many different phases of ice there are? A lot, like 6 or so different phases of ice depending on the temperature and the pressure. 1 atmosphere of pressure, there aren't that many. And so let's go maybe from minus 20 degrees C. So I have some cold ice. Ice, when I add heat to that, what happens? Well, no, it doesn't start to melt. If I add heat to a block of ice at minus 20 degrees, it will warm up. It's going to warm up. What's the maximum temperature of ice? 0. So as I add heat to this, this is called an object. When we have an object, the amount of heat is given by the amount times C times delta T. And so the ice warms. But when we get to 0 degrees C, if I add heat, does it continue to warm? No, it starts to melt. And so as I add heat here, the temperature actually stays the same. But I got to add a lot of heat to melt all the ice. And so I add a lot of heat to melt all the ice. Well, what is the heat given by? The amount of heat that's required to melt the ice is given by what? What's the equation for a process or a phase change? Or it's the amount times H, and delta H. This would be delta H of fusion, which we call melting. And so, you know, I know you've done these calculations before, in intro, and this calculation before. But all I'm doing is I'm saying that we have 2 different Qs. One Q we use for reactions of processes, there's no temperature change. One Q we use when we're heating or cooling an object, the temperature changes. And so once we've melted all the ice, then we have liquid water. And liquid water would be an object. What's going to happen as we warm the water? It's going to absorb heat. It's going to warm up to a max temperature of 100 degrees C. So this is Q of an object. This is Q of a process. So Q of an object here, well, it's just equal to amount times C times delta T. It'd be a temperature change until it gets to a maximum temperature of 100 degrees C. And so here we know we were getting a maximum temperature higher than 100 degrees. It can't go. Water cannot go above 100. What's going to happen is once it hits 100, well, it can if it's not pure. But what's going to happen when it hits 100 is it's going to start to boil. Yeah, boil into steam at 100. And so the amount of heat required to boil the water is given by the amount times delta H of vaporization, which we saw yesterday. Once you've vaporized all the water to steam, then that steam is going to be at 100 degrees C. If I continue adding heat, what's going to happen? Well, the steam's going to start to get hotter. We didn't go this far. In fact, we didn't even melt all the ice. We ended up here somewhere. So we started off at water at 25 degrees C, and we added the heat to heat it up to 100, and then we added enough heat to melt some of it, not all of it. So we stopped here. But if we had more heat, let's say the iron block, provided more heat, then we could have melted all the ice, and then if we still had additional heat, we would have done this. And so what I was saying yesterday is the amount. It depends. We were calculating the amount, and if the amount went over 500 grams, then we know that we had more heat than what was required to melt all the ice. Does that answer your question?
Yeah.
And so That's no problem. When you have melting and when you have boiling, that's no problem. But what happens when you have a chemical reaction, especially a chemical reaction that seems to produce a lot of heat, and the chemical reaction that goes to a very high temperature? Is that chemical reaction at constant temperature? And the answer is what? When I combust methane, is that done at constant temperature? Yes or no? Combustion of methane, is that done? Okay, we have to ask ourselves, yeah, in reality, no, because the temperature skyrockets. But in terms of thermodynamics, is the combustion of methane at constant temperature, or does the temperature increase?
Increase. So I guess the last
Is it constant because it's constant because it combusts at a specific heat temperature?
Thermodynamics is interested in the maximum amount of energy that we're going to get from the combustion. And so the starting temperature and the final temperature have to be the same. What's going to happen is this. If you combust this, at 25 degrees C, and then we make CO2 and H2O gas. Let's say we measure it. Let's say it's measured at 200. Let's say 215 degrees C, some very hot temperature. Did we get the maximum amount of energy from this reaction? No, we didn't. We didn't, because we produced a lot of hot gas. What's that hot gas going to do? Eventually that hot gas is going to cool down. When it cools back down to we end up with H2O liquid instead of H2O gas. When it cools back down to 25 degrees C, where's all that energy going to go? How are we going to cool it? We have to take away the energy from there. And so all that energy is going to go into the surroundings. And so if we stop here, the reaction's not done yet. It's not done releasing all its energy to the surroundings. We've got to wait until it goes all the way here. Thermodynamics deals with state functions. Have you ever heard of state functions before? State functions? State function is an extremely important topic in thermodynamics. In a state function, all we care about is the initial state and the final state. We don't care about how it got there. And so delta t is a state function. Let's say your delta t is plus 100 degrees C. So your initial was at this temperature and your final is 100 degrees C higher. Delta t doesn't care how it gets there. And so you might have started here and then dropped down and then shot back up and then drop down, shot back up and drop down, and finally you come to rest here. That would be your delta t. And so in thermodynamics, we don't stop halfway, We just wait until it goes to the end. And so the point of this is not only this is all the process, a physical process, boiling and fusion. In chemical processes, we have the exact same thing. If we don't have the temperature constant, then both the potential energy and the kinetic energy change. We try to keep our life simple. We try to keep our life simple by, when we look at the total energy is equal to the potential energy plus the kinetic energy. We try to keep our life simple by doing this, U initial, U final. If the temperature is the same, then the kinetic energy is the same. And so there's no change in the kinetic energy. And so delta U here is just the change in potential energy. And so it's not a big deal. We could do the change in kinetic energy. But if we do this, then we have two things we're looking at. We're treating the system as both a reaction and an object. The reaction is going to take place between methane and oxygen. It's going to generate heat to produce CO2 and water. And the object part of this is you have hot objects, hot CO2, hot water, that's going to cool down to cold CO2 and cold water. And so we have to have two different Qs for this. We have to have a Q for the, actually, for the potential energy change and a Q for the kinetic energy change. The Q for the potential energy change is what I call Q of the reaction or process. The Q of the kinetic energy change is what I call Q of the object. But I didn't call it potential energy and kinetic energy. I just called it reaction process or object. Does that make sense? Thermodynamics is not easy. A lot of people find thermodynamics to be the most challenging topic in chemistry. You know, the organic's tough, but organic's a lot of memorization. So people who have difficulty memorizing things will have a tough time in organic for sure, because nomenclature, just nomenclature alone requires tons of memorization. You know, and that's just, you can't get around it. It's just straight memorization. Right? Thermodynamics is a little different because thermodynamics, you have to memorize a whole bunch of definitions. A lot of people don't like memorizing definitions, and also you have to memorize a lot of restrictions on equations. Like you can use this equation under these circumstances. But we're already starting. I'm already slowly starting to get into it. I'm slowly getting into it because right now I'm talking about things like the potential, the kinetic, and then pretty soon we're going to be talking about constant volume and constant pressure a lot more. You know, there's certain equations that you can use under constant pressure conditions, but you can't use under constant volume conditions. We already saw that in mixtures of gases, Avogadro's versus Dalton's. Well, thermodynamics is full of those things that we got to keep track of. You know, when can I use this? Is this valid at all times? Like we call it the volume fraction. Is the volume fraction valid for a gas at all times? The volume fraction. So is the volume fraction of a gas valid at all times? No. When is it not valid? When is it valid? Those are the types of things you have to keep track of in thermodynamics. You have to keep track, and that's what makes thermodynamics so tough, because nobody wants to keep track of that. Everybody just wants to use the equation. I want to just use the equation. I just want to plug this in and plug that in, or I just want some number. You know, this would be the volume. This is what we call the volume fraction. The volume percentage, we just multiply by 100%, and that gives us the volume percentage. So, for example, the vapor pressures of water. What was the vapor pressure of water at 26 degrees C? It was something like 25, something like that, millimeters of mercury. 25 point whatever. This is a fixed number, but why don't we have it the volume? Can I say how many liters that is instead? Oh, maybe get it. Well, anyway, just realize that thermodynamics is a tough chapter. A lot of people have a hard time with thermodynamics, but the thing to do about thermodynamics is to start, you know, with the first definitions and get those memorized, and as we go along, just continue to memorize everything. So Q, W, etc. We're going to memorize. The restrictions are going to come soon. And so I told you QV versus QP. QV and QP. If I combust 1 mole of methane, if I combust 1 mole of methane, is QV and QP the same thing? Is the amount of heat I get the same? Well, that's what we're going to look at next. It turns out that it's going to be different. QP and QV are different. And so, so many things to keep track of. So if this is confusing, it's going to be confusing. Thermodynamics is always confusing. And what you have to do is you have to go home and sort it out in your head so that you have all the definitions straight. Well, same thing with this. Object versus reaction or process. This is always confusing too. You don't know how many people try to do delta T. When I ask them how many joules of energy is it going to require to boil 50 grams of water, so many people put MC delta T because they've memorized Q equals MC delta T. And they try to use Q equals MC delta T for every single problem. Is that going to work? Absolutely not. It's going to fail for certain things. It's going to work for other things. So this is the start. We're starting to learn the restrictions on the equations of thermodynamics. All right. So anyway, today's experiment is a thermodynamics experiment.
We're going to go over some problems on Monday.
Problems with what?
With thermodynamics. Or can we look for something to go over?
Well, like the problem we did go over a problem with thermodynamics, did we? 500 grams of iron? Right. We're going to continue that. In fact, we're going to go over it again today, except I'm going to change some things to it. And so we're going to continue the problem. We're just building up thermodynamics slowly. I'm just giving you a little preview because, you know, a lot of people think thermodynamics is easy because they don't, or they haven't had to deal with all the other stuff. It's like gases. A lot of people think gases are easy because of the ideal gas law, but there's something called the real gas law, which I'll talk about. I still need to talk about that on Monday. Monday I'll talk about it. Well, anyway, don't worry, you know, about thermodynamics yet because we're just starting it, and so I expect nobody to know much of anything about thermodynamics right now. You know. But just be prepared mentally because it's not easy. All right. What we're gonna do today is let's talk briefly about experiment 18. Experiment 18. You know, I'm gonna check those off. And what am I going to do about the observations? You're going to keep your observations. You know, I'm not going to look at those until the very end, but then I'm just looking at your notebook. Instead, what I want to do is I want you to take this little mini quiz. We're going to have a mini quiz. The mini quiz is I just want to see what your observations are for these. So, what were your observations? For these three reactions. The first reaction is going to be Cu solid plus Br2. You know, Br2 in the table is Br2 liquid, but we use Br2 aqueous. Br2 aqueous is going to be less powerful of an oxidizer than Br2 liquid, but it's still powerful enough, and so we'll have it retain its position. Okay, the second reaction I want you to tell me your observations was CuBr2 plus aqueous ammonia. The third reaction I want you to do is Pb solid plus HCl. All right, so just go ahead and write down your observations. This is individual work. This is not group. And so just tell me what you wrote down for your observations for this. So for the observations for these, you could write down, were those kind of expected observations? Or did some unexpected observations occur with these reactions? And just explain it a little bit. All right, so this is just a mini quiz. It's not worth that much. I just want to see what people have written down for observations.